Hello guys, what's up? I'm Mohammad Fuad back with another video about programming. Welcome to the fourth episode of our machine learning course. If you are new here, the only thing that you've got to do is to hit the subscribe button to hop on this course. Alright, so before I tell you what we're gonna be learning today, let me have a recap of what we've learned previously in the first three episodes that we already had. So, the first episode we've learned different types of machine learning such as supervised learning, unsupervised learning, regression, classification, and stuff like that. In the second episode, we've learned a bunch about how linear regression works, and more importantly, we've learned about the cost function, which is really important both in machine learning and in neural networks. In the third episode, we've learned a really well-known and important algorithm called gradient descent, which will help us in all the things that we're going to learn in this course. So today we're going to be tweaking that a little bit and learn how gradient descent works for linear regression. Alright, so now that you know what we're going to be learning today, let's dive right into it. Alright, so before I tell you how the gradient descent algorithm looks for linear regression specifically, let me write a bunch of things that we've learned previously. So we've learned that in linear regression we have a function called hypothesis, which mathematically looks like this. The function h of theta is equal to theta 0 multiplied by x0 plus theta 1 multiplied by x1 and so on. As I said previously, these theta values are the ones that we are trying to learn to find the best ones, so this mathematical function fits our data really well. Then I talked about what a cost function is, and it basically is a measure of how accurate we are with our hypothesis function according to the data that we have. So the cost function looks like this. So this is how the cost function looks, and the other name for it is the square error function. Then we talked about how we use the cost function and the gradient descent algorithm to make a better hypothesis that fits our data even better. And the gradient descent algorithm looks like this. So as you can see, this is the gradient descent algorithm, and it uses derivative, and more specifically the partial derivative of the cost function graph against the theta values. And we talked about what the alpha or the learning rate is, and how basically this gradient descent algorithm works to find the minimum point in our quadratic function, which our cost function makes against the theta values. So now let's see how this gradient descent algorithm will work for linear regression specifically. We have to combine the hypothesis, the cost function, and the gradient descent algorithm itself to make the one that we want. Alright, so as you can see here, we are saying the derivative of the cost function j of theta. And the j of theta is the function which looks like this. So as the first step, let's write this instead of this. Alright, so as you can see, this term over here is equal to this term over here. And so we are currently missing this part over here, which is basically alpha times the derivative of our cost function minus from the theta value that we already have. So we are currently missing that. After we find out what the final version of this here looks like, then we're gonna replace that by this term over here and add these values to it as well. Alright, so now what we're gonna do is we're gonna open this bracket over here. As you can see, it's this bracket to the power of 2. We're just gonna open it and say this bracket multiplied by the same bracket, which basically means that bracket to the power of 2. Alright, that's what we're gonna do. So we're gonna say that is equal to 2 multiplied by 1 over 2. Now this term over here is equal to 1. So we don't need to count that. I'm just writing here for the next line that we're going to use it. So as you can see, we have this bracket multiplied by the derivative of this bracket, which is basically equal to the derivative of this bracket to the power of 2. That's basically what we are saying here. We just open the brackets. Now we go to the next line and implement this over here. Guys, one important note that I forgot to tell you is that all of these equations that we are writing here are all for theta 1, theta 2, and so on. The theta 0 equation is different from this. Alright guys, so as you can see, this hypothesis theta here, this term over here, is basically this term over here. So what this means here is basically theta 1 x1 plus theta 2 x2, and the term n is basically our input values or our features, the number of our features. If we calculate this whole term over here, it will be equal to xj. So let me write that over here for you. Alright, so this is how gradient descent looks like for only one example. So as you remember, I said we have multiple examples in our data sheet, and the number of them is equal to m, right? So this equation that we finally got into is only for one feature, for only one data set. So for only one x, y, for only one of them, and it doesn't count theta 0. So now let's use these to find out how the equation for theta 0 and for multiple examples looks like. In that scenario, we say repeat until convergence, and technically speaking, this is gonna be a for loop in our programming part, and we're gonna say theta 0 will equal to theta 0 minus the alpha or the learning rate times 1 over our training examples multiplied by the sum of our hypothesis function minus the actual answer that we were supposed to get. And for theta 1, we'll have theta 1 is equal to theta 1 minus alpha 1 over m I to 1, the hypothesis theta function of xi minus yi multiplied by xi. So as you can see, for theta 0, we don't calculate the derivative because, as I said, x0 is equal to 1 and theta 0 is basically a number. So theta 0 multiplied by x0 is always a number which is basically equal to theta 0. So that's why we have x0, but our actual input features starts from x1. So that's why we don't calculate the derivative for theta 0. And as we saw, if we want to calculate the derivative for other features, we will end up by this equation over here. So this for loop or formula over here is basically the gradient descent algorithm for linear regression. Alright, this is the end of the episode. It was kind of a short episode compared to the previous ones that we had, but I hope you've learned the gradient descent algorithm for linear regression. And in the next episode, we probably are gonna learn about multiple features and stuff like that. And that's it. If you've enjoyed, hit the subscribe button and the like button, and comment something down below if you have any questions or anything like that. I'll try my best to answer you, and have a nice day.